Now that we've seen flow problems, the max flow problem and the min cost flow problem, and we've seen cup problems, we're going to see how to use them as modeling tools. The first thing we're going to model is the shortest path problem. We've seen the shortest path problem and we proved a few properties about it, but we never saw an algorithm for how to solve the shortest path problem. In essence, what we're going to do is we're going to reduce the shortest path problem to a min cost flow problem. That is, we're going to encode the shortest path problem as a min cost flow problem and then solve that min cost flow problem. In order to encode this problem, we need to find cost, capacities, and demands on this network so that the min cost flow in this network maps to a shortest path in our original problem. To do this mapping, the idea is that we're going to send one unit of flow from S to T along all the arcs so that it never splits, and this one unit of flow, as it moves through the network, is going to be exactly the shortest path. To do this, we need to send one unit of flow from S to T, meaning that the demand at S is going to be -1 and the demand at T is going to be 1. The demand at all the other nodes is going to be 0. The capacity along each one of these arcs is going to be 1, as we can only send one unit of flow across each one of these arcs. In this way, that one unit of flow is going to match exactly to choosing that arc inside of our shortest path. The cost on in our new min cost flow network are going to map exactly to the cost in our original path problem. We're going to have 1, 3, 2, 5, and 2 on each one of these arcs. It's a simple exercise to show that any min cost flow inside of this new network that we drew matches exactly to a shortest path in our original problem. It's perhaps not too surprising that we can model the shortest path problem as a min cost flow problem. The two linear programs, or integer programs, look very similar to one another, and the problems themselves have the same idea. They work on graphs. What's interesting is that we can model many diverse problems as flow problems. Here we have a particular problem, a scheduling problem, that doesn't look initially anything like a flow problem, but we'll see that it is identical to a flow problem, or can be modeled as one. In the scheduling problem, we're given n jobs, indexed by j, and m processors, indexed by p. Each processor has a maximum number of tasks it can execute, or jobs rather. We're going to denote this by capital T of P. We're also going to have an availability graph. The availability graph tells us which jobs can be processed on which processors. Specifically, we have our node set J and our node set P, and an arc is between little j and little p when P can process J. If the arc doesn't exist, then P can't process J. The objective is to assign jobs to processors so that each processor isn't overloaded, that is, each processor is running at most capital TP jobs, and the job J is assigned to P only when the edge JP is in our availability graph. We can model this as a maximum flow problem. The idea is that we're going to create an initial dummy node S and a terminal dummy node T, and in the middle we're going to have our graph of availability. Here we'll have a particular example of availability graph. The availability graph tells us when a job can be processed on a particular processor. The actual details of this graph don't matter. Any availability graph can go in the middle. And now what we'd like to do is say that each one of these jobs is going to have one unit of flow available to it, and that one unit of flow is going to go to exactly one processor, and that processor has to be linked to this job through the availability graph. To get that one unit of flow to the job, we're going to have an arc from S to the job for each one of the jobs. The capacity along each one of these arcs, Uij, is equal to 1 inside of this region. Inside of the availability graph, we turn the availability graph into a directed one, where the arcs are pointing from the jobs to the processors, and we set the capacity on each one of these arcs equal to 1. That is, this one unit of flow on this job can only go to exactly one processor. Finally, there's some flow left on these processors that we have to get to T. So we have to draw arcs from each one of the processors to T. along each one of these arcs, we'd like the maximum amount of flow along each one of these arcs to be capital T of P. This encodes that if we have some number of jobs going into our processor, that the number of jobs whose flow is flowing through the processor is at most capital T of P. That's because the maximum flow that can come out of each one of these processors is exactly capital T of P, so the amount of flow into these processors can be at most T of P. This graph then encodes this scheduling problem. To solve the maximum flow in this problem, it's a simple exercise to go from this maximum flow back to this schedule.